All right. Thanks everyone for tuning in to another episode of the F Word Programming in Fortran. Today we're going to be talking about some differential geometry and a topic known as the metric identities, or in some worlds we call it free stream preservation. The material that we're basing today's whiteboarding session on really comes from these two papers. The first one from David Kopriva on the metric identities for spectral element methods, in particular on curvilinear meshes. And I mean, this is a property that's been known for some time. So the other paper here is from Thomas and Lombard in 1979 on geometric conservation law. They both refer to the same thing here, but a lot of the material that we'll be talking about today comes from those two sources. And I put the links to those papers down below in the description in case you're interested. And there's also a set of notes that you can get to from the Open Collective page that go along with the lecture today. So let's talk about the problem at hand that we're trying to solve here. So when we're doing spectral element methods, essentially what we do is divide up space into elements, and on the left hand side here what I'm showing is like a 2D slice through a 3D mesh. And if we do that slice, what we look at are quadrilaterals here. But of course, if you think about extruding this into 3 dimensions, what we have are hexahedra. And the sides of each of these elements, so the elements being each of these logically, in this picture, quadrilateral spaces that are enclosed by 4 sides. What we do in practice is essentially keep track of mappings from the physical space, so from something with curved sides here to computational space, which is something that would have straight-sided, more or less like a straight-sided domain. And in the process of doing that mapping from one coordinate system to another, you can use differential geometry to come up with formulas that tell you how to calculate derivative operations in physical space, provided you know that mapping and you know how to calculate derivatives in a computational space. Now the problem is, if you're not very careful, what can happen is you can basically develop spurious flows, even if you have a scenario like what's shown on the right hand side. This is in this particular example from Kopriva's paper in 2006. They're solving the compressible Euler equations in 3D, and they have a uniform flow set up that's going from left to right in this scenario. But if you have a uniform flow and uniform density field, there shouldn't be much that happens. In fact, the field should just stay as it is. You shouldn't develop any sort of flow because of this. Now, unfortunately, if you don't satisfy the metric identities, which is what we'll talk about here in a minute, you can develop these sort of spurious flows that are really tied to features of the mesh. Now, although the errors that you incur in the spectral element methods are spectrally accurate, of course, having this sort of noise in your solution, or these spurious sound waves in this particular case, is not ideal. And so what we're going to talk about is a way to calculate the metric terms so that we don't have spurious generation of sound waves in the Euler case, where if you're doing like advection problems, you're not just generating noise in your data in your solution simply because you have a mesh that has curvilinear sides. Okay. So we'll take a step back here and talk about how these mapping actually happens, and then we'll talk about a very clever formulation that you can use to make sure that your metric terms are divergence-free. And when they're divergence-free, it turns out that that's the property we need to have satisfied so that we don't generate these spurious flows. So what we're doing, remember where all this is coming from, is we are trying to solve a conservation law, ds dt plus the divergence of a flux vector equals some source term on the right hand side. And the trick here is figuring out how we're going to calculate that flux divergence in physical space, given that we're going to basically divide, let's go back to this picture here, we'll divide space up into elements with, in 2D, 4 sides, in 3D we'll have 6 sides, we'll do quadrilaterals and hexahedra. And then those elements themselves will have curved sides. So the question is, how do we calculate these? Now, if you've seen these videos before, you know that essentially what we end up with is being able to rewrite this equation, it looks almost identical. The divergence we calculate in computational coordinates, and I'm going to use the squiggly over arrows for our vectors here to indicate that we've done a coordinate transformation. The equation essentially looks the same, and what we have is the solution vector is just the Jacobian weighted solution vector, the Jacobian of the coordinate transformation, and then the flux vector ends up being the contravariant weighted, the contravariant vector weighted flux. So today we're going to talk about where this comes from, so you have a little bit better feel of how that transformation actually happens. And then specifically what we'll need to pay attention to is how we actually calculate these contravariant terms. Now the reason why we got to be careful, and I'm just trying to give you an overview of the problem here, what we need to have is that if for example, if that flux vector is a constant, so let's say f is a constant here, we know that the divergence of that constant vector is got to be 0, and we want to make sure that that property is maintained even when we go under a coordinate transformation. So if I were to write the divergence of f under my coordinate transformation, what I have is the divergence in computational space, and I have the Jacobian weighted flux vector is going to be equal to 0. Now if f is a constant, I can pull that outside of the derivative operator, and what I have to make sure that I satisfy is the divergence of the contravariant basis vectors. The Jacobian weighted contravariant basis vectors has got to be 0. So this is, if you wanted to get the TLDR here, is this is what we end up wanting to prove, and there's a very special way we can calculate those terms to make sure that this property is maintained. This is really what we're after. So let's talk about how we get there. So the first thing here, it's kind of subtle. What we have in practice is a mapping that takes us from computational space, so from a nice, like in this example, a hexahedra on -1 to 1 in each direction, and it brings us to physical space, right? So I know this mapping. I know x. You give me a computational coordinate, I can give you out a physical coordinate. Now, but the problem is what I need to be able to do is I need to calculate a derivative in physical coordinates, right? So like if I wanted to take the derivative of a function with respect to x, a physical coordinate, but all I know how to do is actually calculate derivatives in computational coordinates, and then I know this mapping. Now, of course, I can use chain rule. I can write this out. What I have is, if I were just to basically say that, okay, let's pretend for a moment, maybe I do know c as a function of x. What we have to do from here is, right, if we apply a chain rule, we get df dxc1, dxc1 dx. I got df dxc2. Sorry, I got a dog here. Df dxc2, dxc2 dx. And then df dxc3, dxc3 dx, where these c's, the c1, c2, and c3 are my computational coordinates. Okay, so if I wanted to write this shorthand, I can just write the gradient of f in the computational coordinates dotted with, dotted with dxc vector dx. But like I said, all I know on the outset is x is a function of c, so I don't readily know how to calculate dxc dx, dxc2 dx, etc. Okay? Now, of course, we can extend this idea, right? If I want to calculate a gradient, I have a df dx, df dy, df dz, right? Same idea applies. If I have a vector and I want to calculate a divergence of it, we can do a similar thing. So, for example, if I want to calculate divergence of f in physical coordinates, what I have is that sum I equals 1 to 3 if I have df vector dci, and then I would just dot that with gradient of ci. All I'm trying to illustrate here is essentially, this is what we ultimately want to calculate, but we need to figure out how we can actually calculate those given the fact that we only have the coordinate transformation that takes us from computational to physical space. Okay? Okay, so the first thing I want to point out These terms here, these grad ci, are what are called the contravariant basis vectors. And we're actually going to show how you compute those if you know what the covariant basis vectors are. And the covariant basis vectors are the ones that we can readily calculate. So the covariant basis vectors, let me get us some space here. Covariant basis vectors are the derivatives of that coordinate transformation with respect to each of those computational coordinates. So the covariant basis vectors are dx, dxc, I. So we'll write this as A with a subscript I. And then as we go through this, you'll start to see the relationship that these have with the contravariant basis vectors. So ultimately, we're going to use these together in a very clever way to figure out how to actually do those sort of chain rules that we just did. Okay, so we need to start from maybe a little bit of a weird spot, and then we're going to use divergence theorem to back out what these are. So let's first talk about how to construct a little bit of a unit of length. So this might seem a little bit silly, but a little bit of a unit of length in physical space I can write as the sum I equals 1 to 3 dx dxc I, and then if I multiply that by a small little unit delta I, so I could even write delta on the left hand side. I suppose it doesn't matter, let's just use d's. So a little increment in space, and I can calculate, if I know how to do these changes, if I know how to calculate these guys here, I can calculate arc lengths. So for example, if you wanted to get an arc length out of this, what you could do is just calculate the magnitude of this vector. So for example, if I did the magnitude of dx, right, I can get out of this the sum I equals 1 to 3. We'll get another sum here because I'm going to dot with basically dot the vector with itself. To get the ideas, essentially we can get a unit of length out of this. Now if I want to get a little bit of an area out of this, what I can do is if I calculate a little bit of a unit of length in one direction, so let's say this is the dx dxj, and if I have the other covariant basis vector dx dxci going in another, this is j, and then we'll call this one k. If I multiply that by dxck, multiply this guy by dxcj, if I take the cross product of those two vectors, right, I can get the area of the parallelogram that's spanned by those two vectors, right? That's just from linear algebra, if you remember that. So if I want to get a little bit of a unit of area, what I can do, so dA with a subscript I, is what we're going to introduce here is I, j, and k. Well, I will vary from 1 to 3 if we're in 3 dimensions, and these indices will be cyclic. So dAi is just going to be the cross product of dx dxc j dxcj cross dx dxck dxck. So, all right, so all I'm doing here is now that I have a way to calculate a length, if I take the cross product of two of these the covariant basis vectors, I can get a little bit of a unit of area, and the normal, of course, points in this case out of the page here. Okay. Now, if I want to get a small unit of volume out of this, if I dot that area in the direction of that third basis vector, so in other words, if I want a volume, what I'm going to do is take dAi, I'm going to extrude it in the direction of that third covariant basis vector. So I got dAi, and then I've got A sub I delta Ci. Okay, that gives me a way to calculate a little bit of a unit of volume under this coordinate transformation. And in a second, what you're going to see here is we're going to take the idea that we know how to calculate units of area and volume and apply divergence theorem in the computational space to show you how we would calculate divergence given these mappings. Right, so if I write this out, what I'm left with is Aj, and I'm calling this AJ because that comes from that dx dxj. That's our covariant, the jth covariant basis vector. I've got cross with A sub k, and then I've got dotted with A sub I, and then I have out front dxci, dxj, and dxk. Now this first term out in front has a special name. This is the Jacobian of that coordinate transformation that we were working with. All right, so a little bit of a unit of volume I can get by having the Jacobian multiplied by dxci, dxj, and dck. So a shorthand way of writing this is to say that a little unit of volume, which we'll call, dv, it's just going to be j, and then we'll just call it dxc, and I'll put an underbar underneath it to indicate we're doing a volume integration in that computational space, right? And I can also write that as equivalently as dx, where that dx really is dx, dy, dz. Right, so we've done the coordinate transformation, so we have that, and we have a definition of a Jacobian here. So now what we want to do is take a look at how we would calculate a divergence. This is a very easy way, if you know the divergence theorem, to show how we could basically relate the covariant, contravariant basis vectors so that we can apply the sort of chain rule that we had wanted to beforehand. Okay, so if you remember, if you have taken Calculus 3, you may have remembered the definition of a divergence, right? And if you've done Calculus 1 before, you can kind of see where this might come from, except we're doing things in multiple dimensions with vectors. But I have the limit as the volume goes to 0 of an infinitesimal volume of 1 over delta v, so 1 over the size of that volume, and we have the boundary integral over that little region of space we have f dot dA. Okay, so what this really means is what I'm going to do is I'm going to calculate the flux through this side. Okay, I'm going to subtract the flux from this side. I'm going to add the flux from this side. Right, we're just doing the flux dotted with the outward pointing normal, and we're adding up all those terms from each of those faces, and then we're essentially going to shrink this volume down to 0. Okay, now there's a lot of details. I encourage you to check out those notes that are shared in the description down below. When we go through and plug in, for example, let's say on this side, what I'm going to be looking at using is an area that is spanned by the second, so dx dxc2 covariant basis vector, and then we have dx dxc3 on that side. Same thing for this side wall, that side wall. We have dx dxc1 cross with dx dxc3 for those south and the north facing side walls, and then for the bottom and top it'll be dx dxc1 and 2 cross product to get us those units of area there. Essentially, you know what? Might as well go ahead and go through it. Take our time here. What we end up having when we do that area integral. So we have the boundary of v, f dot dA. So if I'm going to do this on, let's say, which side do we want to start with? Let's start with this east-facing wall and the west-facing wall. Okay. What we're going to have is f dot a2 cross A3 for the east-facing wall. Okay, so it's going to be at C1 plus delta C. So let's put a couple labels here. Okay, so over here is the center of this this element here will be C1, C2, C3. So this will be at plus delta C1. I'm not sure why that's not staying there. And then over here, when we go towards the north side, we have plus delta C2, and then let's see here, so let's do it this way. So we got plus delta C2, and then from the top to bottom, what we'll have is we'll have plus delta C3 at the very top. So the bottom corner will be C1, C2, C3. We'll have a side length of delta C1. That's probably a better way to write this. and we'll have a side length here of delta C2, and then we'll have a side length. Boy, I'm not sure why that's disappearing. All right, on this side we'll have a side length of delta C3. Okay, so what we have on the eastern wall here is the evaluation of that vector flux. So we have F dotted with A2 cross A3 at C1 plus delta C, and we have minus F dot A2 cross A3 at C1, okay? And then of course we're gonna be multiplying by delta C2 and delta C3 to get us that total area. Okay, so let's now do the north and south side. So on the north side, what we have is F dotted with, we got C1 and C3 for those areas. Okay, so we have A3 cross A1, just so we get that orientation right. This will be at C, this will be at C2 plus delta C2, and we have minus F dot A3 cross A1 at C2. And this is going to have an area of delta C3, delta C1. And then the last is the bottom and the top, which is going to be the area unit there is going to be formed by A1 and A2. Covariant basis vectors. So we got A1 cross A2 evaluated at C3 plus delta C3 minus F A1 cross A2 at C3. And then the area there is delta C1, delta C2. Okay, now of course remember what we're doing for the limit definition of the divergence, right? That guy was the limit as the volume, the infinitesimal volume delta V goes to 0 of 1 over delta V boundary, the 1 over delta V of the closed boundary area integral of the vector flux. Okay, so we're going to use the fact that delta V is going to be delta C1, sorry, it's going to be Jacobian, delta C1, delta C2, delta C3. Okay, that's our area. Now, when we plug all of this in, all right, so if I were to put a 1 over delta V out front here, what I'm left with is, in this first term, the delta C2 and delta C3 from the volume cancel, and I'm left with the divided by delta C1 on this first term. Okay, and what I'm left with here, the delta C1 and delta C3 cancel, and I'm left with a delta C2 in the denominator. And then in this last one, I'm left with the delta C3 in the denominator. And of course, all the terms are divided by, let's just put 1 over the Jacobian out front there. Okay. All right. So when I apply this limit, right, what I end up getting, if I apply the limit as delta V goes to 0, what I have is the limit as delta C1, delta C2, and delta C3 product all goes to 0. So the first term, if you remember from Calc 1, this is just the definition of the derivative for F dot A1, or sorry, F dot A2 cross A3, and so on. So what we can do is we can rewrite this last term, all of these terms. I'm going to go ahead and clear the board here just so we can kind of summarize this neatly. Is we have a sum I equals 1 to 3. Whoops, I equals 1 to 3 of 1 over j, okay, d dc I f dot a j cross a k. Okay, and this is for I, j, k cyclic. So what that means when I, j, and k are cyclic is when I is 1, j is 2, k is 3. When I is 2, j is 3, k is 1, and so on down the line. All right. So at this point, what we have right, is if I want to calculate the divergence of a vector, so far I had the sum I equals 1 to 3. We're going to clean this up. I'm going to pull that Jacobian out front. D dxi f dot aj cross ak. Okay, so far that's what we have, and now is where we actually get to apply the metric identities. I know that if f is a constant, so we'll say if f is a constant, f is the c vector, it's just a constant field, then I have that the divergence of f is 0. And that's going to mean that 1 over j, sum I equals 1 to 3, d dxi of aj cross ak, right, dotted with c, and I can move that c outside the derivative because it's constant, that has got to be 0. Now for this to be true for any constant vector, that means that this term has to be 0. Okay? So that means that sum I equals 1 to 3 d dxi aj cross ak has got to be 0. All right. Now that statement, we can use this statement to rewrite the metric or the divergence operator in a slightly different form, because this property of any coordinate transformation has to hold. What we can do is we can also write the divergence as the sum I equals 1 to 3. We have df vector dxi dotted with j aj cross ak, where again j is that this capital J is the Jacobian of that coordinate transformation. Oh, sorry, that's actually a 1 over j. I'll just pull that out front. Okay, so now we can actually go back to the chain rule that we had, right? Now the chain rule we had for doing a divergence, let's see, did I have that on the back slide? No, I think I erased it. Now the divergence operator that we had before, what we were trying to do, right, if I were just to flat out just apply a chain rule, I get the sum I equals 1 to 3, okay? I get df vector dxi, and then I get dotted with, let's see here, I have it in my notes here. Da-na-na. What we end up with is dotted with, grad in physical coordinates, dxi, and again, these were the contravariant basis vectors. All right. So what we have is that grad xi, if I compare this form with this form down here, what I have is that the contravariant basis vector grad xi has got to be 1 over j aj cross, aj vector cross with ak. So this is my relationship between the contravariant basis vectors and the covariant basis vectors. A convenient way we usually write this in notation is the covariant basis vectors will use subscripts. The contravariant basis vectors will use superscripts. I'm going to go ahead and multiply by that j out front. And what I have is j, the Jacobian weighted contravariant basis vectors is aj cross ak. All right. That's our relationship between covariant contravariant basis vectors. This is what allows me to actually do calculations. And what I got for free out of doing this derivation is I have this formulation, this first formulation that I can use to write my, how I do divergence calculations. So let's rewrite this real quick to summarize where we got. What we have is the divergence of a vector. We can write it as, and I'll put this, the first form is what we call conservative form. It's going to be the sum I equals 1 to 3. Okay, I have 1 over j out front, d dxi, j a I dotted with f. Okay, that's the conservative form. Non-conservative form, what I end up having is sum I equals 1 to 3 df vector dci dotted with a superscript I, in other words, a contravariant basis vector. And again, that was the same thing as aj cross ak. All right, so you could come up with similar rules for gradients. So if I were to write a gradient in conservative form, I can do sum I equals 1 to 3, got the 1 over j out front, d dxi, j a I f, if f is a scalar here. This is how I would calculate a gradient. If I wanted to do a curl, you can also show you have 1 over j sum I equals 1 to 3, d dci, j a I cross f. I promise you I'll get to the point here in terms of where the problem comes in. Remember, the issue is if I'm not careful how I calculate, right? So what I need to end up calculating to do divergence calculations, to do conservation law solvers, in other words, to do Euler equations, Navier-Stokes, what have you, what I need to be able to do is really calculate these Jacobian weighted contravariant basis vectors, because those are used in that formula there. If I'm not careful about how I compute those, we get spurious flows when you have curved geometries, okay? And that's what Kopriva showed in 2006. Thomas and Lombard had discussed this issue at length. This has always been something that folks care about when developing methods, is making sure you calculate those metric terms carefully so that you don't get, like he's showing here in this case, these spurious sound waves that are being generated. So where this comes up as a problem in spectral element methods is it really is rooted in the fact that in 3D specifically, when I go to calculate the Jacobian weighted contravariant basis vectors, typically the coordinate transformation, basically where I go from computational to physical space, the points where I evaluate that mapping, right? Since I'm doing everything as an interpolant, a polynomial of degree n, each of these terms are polynomials of degree n, and if I take a cross product of those two together, what I get is a polynomial of degree 2n. And if I co-locate my contravariant basis vectors on the degree n grid, unfortunately I incur an aliasing error, and I don't satisfy the metric identity. So that's where that problem really comes from, is from the fact that this term is a polynomial of degree n, as well as this, so the product of them is a polynomial of degree 2n, and for collocation type methods, this causes problems. So what's the solve here? How do we fix this? There's a couple clever things we can do. So I did cover metric identities all in one slide, so we'll skip over here to the conservative and Curl-invariant forms. The deal is, you know, what we want to have happen for the metric identities, right, is the sum I equals 1 to 3 JAI equals 0. This is the same thing as saying sum I equals 1 to 3 AJ cross AK is 0. And again, I, J, and K are cyclic. Okay, so this is what we want to have satisfied. If we remember, we can also write this as dx vector dxcj cross dx vector dxck. So we're going to use a little bit of a cheat from vector calculus to help us come up with a way to make sure that no matter what, even if I'm co-locating and incurring aliasing errors, that I can guarantee that this always equals 0. Okay. So if you remember from vector calculus, when you're working with the curl of a gradient, the curl of a gradient is always 0. And we can actually use this to our advantage because you can also show that the divergence of a curl is always 0. So we're going to use those two bits here to reformulate how we calculate this term so that when I do things discretely, no matter what, I'll always have the metric terms written as the curl of a vector. because if I write the metric terms as the curl of a vector, taking the divergence of that goes to 0, so I satisfy the metric identities. So if you remember, if I have two functions u and v, and I have grad u cross grad v, I can write this in two different ways using a product rule essentially, and the fact that the curl of a gradient is 0. So the first way we can write this is the negative of the curl v grad u. Okay. The other way we can write this is the curl of u grad v. Oops. U grad v. And of course there's a third way, right? I mean, I guess there's really infinitely many, but another way to write this is to do the average of the two. So I can do 1/2 curl of u grad v minus v grad u. All I'm doing is just manipulating things in such a way that I can write this cross product of two gradients as the curl of something. And the reason why I'm doing that again is because no matter what, if I were to take the divergence of a curl, so grad u cross grad v, right, that's going to be the divergence of, if I put that negative sign up front, curl of v grad u. Doesn't matter what I'm taking the curl of. If I take the curl of it, it's always going to be 0. All right, and that's the property we want to have. Because if I have that, so the trick is in understanding how we can write these terms as something that looks a little bit more like this. Okay, so that's what we're going to do here. All right, so first, if I were to say, so let's clear this up here. All right, so we're going to use this rule. And what I can do is if I were to take a gradient in computational space of the mth component of a vector, so like if I were to think about writing this as x sub I hat xi, right, the mth component of the physical coordinate mapping vector, if I were to cross that with the gradient in computational space with xl, right, we can write out each of those terms there, right? So if you've done cross products before, for that first term, what we'll get is dxm dxc2, dxl dxc3, then I've got minus dxm dxc3, and then dxl dxc2. All right, that's the first that's the first one. The second term, or the second component of that vector is dxm dxc1, dxl dxc3, minus dxm dxc3, and then dxl dxc1. That's our second component. The third component, if I'm doing that cross product, is dxm dxc1, dxl, oops, come on now. Here we go. dxl dxc2 minus, a little sloppy there, minus dxm dxc2, dxl dxc1. That's our third component, okay? So let's keep that in mind, okay? And now if we're careful, I'm just going to do the first term here just because I could show you the equivalence between something like this and the contravariant basis vectors. So if I were to do JA11, so the first component of the first contravariant basis vector, what that ends up looking like is dx2 dx, that's going to be 2 dx3. What are we going to have here? We're going to have so dx3, yeah, that'll be dxc3, and then dx3 dxc2, and then dx2 dxc3. Okay, so if I were to look at taking So in this first equation up here, so in this first equation, if I were to say n, m, and l, those indices were cyclic and n were 1, if n were 1, m would be 2, l would be 3. So up here I would replace this m with 2, this l with 3. Hey, that matches up with 2 and 3 down here. I've got 2 and 3 in those in the bottom derivatives there. I've got 2 and 3 here, and I got 3 and 2 there, but the derivatives, you know, a times b is b times a. I can actually match up components of each of the components of each of the contravariant basis vectors to a formula that looks like this. And in general, what that formula looks like is the nth component of the ith contravariant basis vector I can write as xi dotted with grad in the computational space xm cross grad c xl. Okay, so I have a way to express how to calculate the contravariant basis vector in terms of grad u cross grad v, which we just showed what we can actually do. Sorry about that. What we can actually do is write grad u cross grad v, right, as the curl of something. So I now have 3 different ways I can write the contravariant basis vectors. Okay, so what we can also do here, right, is if I were to think about writing in terms of that curl-invariant form where I add, so remember what we have, grad u cross grad v, we can write as 1/2 curl of u grad v minus v grad u. Okay, and if I were to sub in for u x sub m and for v x sub l, I can rewrite this formula down here as xi dot 1/2, which will move that out front, curl of u, which is going to be xm. So you have xm grad xl minus xl grad xm. Okay, so now I have a way to calculate my contravariant basis vectors as the curl of something, which whenever I take a divergence of that, I end up with 0. So that ends up working out pretty nicely for us. This is essentially what's called the curl-invariant form. So although in practice, yeah, I could go into the code, right, and calculate essentially each of these terms in this form, unfortunately, when we calculate the metric terms, the contravariant basis vectors in this form, because of aliasing errors, the divergence of this turns out not to be 0 in the discrete system. However, if I calculate them using this formulation, although on paper in the continuous form these things are identical, in discrete form they're different. They're both spectrally accurate, but this one actually preserves the metric identities. So this is what we're actually going to be looking to implement in self for the 3D metric terms, because it turns out actually in 2D you don't have, this is actually not an issue to worry about. And if you check out that paper from Kopriva in 2006, you'll see why that is. So we don't need to do anything in the 2D metric term calculation, but we do need to modify the 3D to calculate this. Now before we do that, I think what I'm going to end up doing today is just going through and implementing a 3D model to show that we can actually recreate this problem. And then in between this video and the next one, I'll be sharing some updates here and there on Open Collective. And if you follow us on LinkedIn and Reddit, you'll see some updates come across in the next couple weeks where we get this implemented and show we can actually satisfy metric identities. So let's go ahead and switch gears here. We're going to hop into self and take a look at implementing a 3D model. I'll sketch out what we need to do as the next couple steps to get these metric terms calculated in there. So we'll get that sort of documented and put on the to-do list. So let me go ahead and jump over now. All right. So there's a couple spots that we need to focus on in order to, one, demonstrate this problem so that we can show that when we implement the curl-invariant form, we indeed remove this issue. The first thing is, so if you're not familiar with self, I'll give you a brief rundown. Everything in self is built on top of one, it's called the memory class, self-memory. And the memory class is just a way to provide multi-dimensional arrays in Fortran on the CPU side and C pointers to device data so that you can operate both on the CPU and GPU. It provides some methods so that you can map between host and device, so CPU and GPU. That's at the very bottom, and then we have a few support routines, things that calculate quadrature for us, so we can basically create nodal points and quadrature values for doing integration with either Gauss or Gauss-Lobato using either the Legendre or Chebyshev bases. Now on top of the memory and the quadrature, we have really the workhorse of self is the Lagrange class. Now, everything in self operates on the idea that we're dividing space into elements, and within those elements we're treating the solution as a polynomial interpolant. And the interpolation points are set to be exactly the quadrature points, which has some very nice properties. You can learn more about that if you scroll back through some of our previous videos. So on top of the Lagrange class gives us the mechanisms to calculate and do things like interpolate, of course, but we can also use that class to do derivative operations. And this is where we do derivatives in what I was referring to as computational space. Now on top of the Lagrange class, we have a data class. Now that data class is the thing that really starts to set the stage in terms of objects that are I guess closer to the methods that you might use. So in general, what we're thinking of is we want to be able to do derivative and interpolation operations on scalars, mathematical scalars, vectors, and tensors. And so those data objects are laid out there. And in spectra elements, what you're generally working with are nodal points that are interior to the element, nodal points that are on the element boundaries so that you can share data between neighboring elements. And then you have some other properties like the average value along a face or the jump across a face so that you can use those kinds of things in Riemann solvers. The other property that you're looking at here is this ext boundary. So if you actually have a physical boundary, you might want to impose what the function should be on that physical boundary. So it's a mechanism for enforcing a boundary condition. Now once you have data, the other key ingredient here is a mesh. Now the mesh, we work with unstructured meshes, which essentially means that I have a list of nodes that define space, and then I have edges that connect those nodes. I have that connectivity. And then I have edges that make up faces in 3D, for example, and then faces together that make up an element. Now all the elements we work with in self are what are called tensor product elements. So in 1D it's a line segment, 2D it's logically a quadrilateral, so it's a cross product of a line segment with another line segment. And in 3D it's a hexahedra, so think about taking a cross product, just like we did with those the volume term in the when we were doing the divergence theorem. We're just basically doing another tensor product with a third dimension, so you end up with a hexahedra. So we have an unstructured placement of hexahedra in 3D, unstructured placement of quads in 2D. That make up the mesh. Now the other element there is each of those spectral elements, they have geometry. And that's the bit that we worked out today that defines how to go from computational space to physical space. So it's in that geometry class where we end up needing to put this new curl-invariant form for the metric terms. So if you look in the geometry class, there's geometry 1D, then there's quads and hexes. And we've got those physical positions. So this is our actual coordinate transformation, those covariant basis vectors, contravariant basis vectors. There's a convenience vector that we use for the boundary normals. So on the faces of the elements, on those side walls, we have an outward pointing normalized vector, which is useful for doing Riemann solver calculations. And then we have the magnitude that was pulled out when we did that, so you can actually do area integrals over surfaces. And of course, that Jacobian of that coordinate transformation. Now, if you look at the type-bound procedures for this method, we have, of course, an initializer, a finalization routine, which is just frees all the memory associated with that object. We have some additional tools here to help with the mesh generation process. So if someone provides a mesh, I can actually go through and calculate all those metric terms. And this is where we end up needing to do some of the changes. So particularly underneath calculate metric terms, that we call calculate contravariant bases. This is the one that we end up needing to modify. Okay, and right now, what we're actually doing, let me actually jump to bases, SEM hex. What we do here, right, is really just work with that initial form. We're basically doing the grad U cross grad V. What we want to do essentially at this point is convert this from grad U cross grad V to this Curl-invariant form that Kopriva talked about in his 2006 paper. So we've got it marked as to do here. Now there's a couple ways we can do it. The thing I actually need to have underneath the hood to make this work is I need to be able to calculate a curl. And the thing I need to be able to calculate a curl of what we have is curl of xm, grad xl, right, minus xl grad xm. And if we take a look real quick, what we're calculating gradients of inside this formula are the physical coordinate positions, right? So if I calculate gradient of xm, I multiply by xl, calculate gradient of xl, multiply by xm. What I have inside of here is a vector. So one, I think what I can do is actually go ahead and calculate this vector very straightforward. Let's take a look at the SEM hex class. So for example, x is a vector. Already, I can calculate a new vector, right, just by calculating the inside of that curl operation and get another vector out. But now I need to calculate a curl of a vector. And these are the vector 3D class. So let's take a look at the self data class. I'm going to take a look at the vector 3D. The vector 3D class currently, I have gradient, and I do have a curl operator, so I should be able to stitch all this together. Yeah, that's actually looking okay. So let's take a look down here. I really wish I had more time to plan out what I'm doing here, but thanks for tagging along. William, I'm so glad you're a fan of vector calculus. This is one of my favorite subjects when I was in undergrad. It's a blast. All right. No, we want the SEM hex class. All right, so what we need to do is we need a new vector. Let's open up another window here. So let's edit the self data class. What I need for a curl is a vector in. I need to send a vector out. Okay. So what I need to do is, so the one that goes out is going to be in the argument, and the one that goes in is the one I'm taking the curl of. So I need, what are we going to call this? We'll call this XMGXL. That'll be fine. And we're going to do a curl. So we've kind of walk ourselves backwards here. Now the output, what I'm going to get from this is curl xmgxl, so we'll call it curl xmgxl. And then we're going to set the GPU acceleration to false on this one. I've been having some issues actually with the mesh generation, some of the mesh generation routines on the GPU, and haven't had the time to actually sift through that. Right. We'll figure out some logic here in terms of swapping this out, but I'm just trying to sketch out what this is going to look like. Because I think what I'm ultimately going to want to do here is come up with an example using the current form that shows all this stuff results in spurious flows, and then we'll enable this stuff, make sure it works, and then we'll add in some bells and whistles to toggle it on and off with command line options or something. Okay, so I've got, if I at the end of this want to have curl xmgxl, and then I have xmgxl, what I need to be able to do is calculate xmgxl. Okay, and boy, there's going to be a few of those. Actually going to have 3 of those to do. So I'm actually going to be working with a tensor here. Okay, so let's do this. I'm going to need a vector 3D, and we'll call it xmgxl, and then we'll have curl xmgxl. All right, and then what we're going to do is I need to initialize those. So let's go ahead and close this. And then SEM hex. So we're going to borrow one of these methods here to initialize. And then let's go back to that contravariant basis, SEM hex. So what we're going to do is initialize xmgxl. Now, remember in the formulation, what I need to do is calculate xm grad xl for n is 1 to 3. So I'm actually going to have 3 variables here. The interp I'm going to pass to it is the same interpolant I'm using for the geometry. So we'll do that. And then the number of elements is going to be the same number of elements that we have for the geometry. So I can just use an elem. All right, so that's that. And so by varying the var dimension, that will help me vary n from 1 to 3. Let's go ahead and copy that. And we're going to do curl of this guy, xmgxl. And again, that one will also be var 1 to 3. And we should be good there. So 1, 2, 3, 4, 5, 6. I'm going to kind of keep all this together. So I'm just going to sketch this out because I think I might end up working out a lot of the details in the coming weeks. But let's do this. So I'll call that n, because we're going to do n ml cyclic. So we'll do n is 1 to 3. Whoops, down here. So 1, we need to calculate grad x. If I actually calculate the gradient, I think I can get a tensor out of that. So let's do this. Do a tensor 3D. We're going to do grad x. And let me just double check that that is possible. Gradient vector 3. I did implement those. That's cool. All right, so if I do a gradient, what I get out, yep, is a tensor. So that's good. That's what we'll do there. So copy that guy. We're going to need another declaration here. We got grad x is what we got there. The input is going to be the geometry, actually, no, the output is going to be grad x. Grad x, we'll set, again, GPU Excel to false. And the input is going to be my geom %x. So those physical coordinate positions we'll use to calculate the gradient. And then let's go take a look at the self-Lagrange class to see what that, whoa, not what I meant to do. Vector gradient, 3D, not 4D. All right, vector gradient, here we go. So here's our output. Got our mapping here, so let's copy this over so we know this. 1, 2, 3, 4, 5, 6, 7. Take those 7 lines. All right, so what we got there, when I get my output for the gradient, I should be able to map things appropriately there, making sure we get those dimensions correct. Let's go ahead and put in a initialization for grad x. This one will do 1 variable because the extra 3 dimensions are actually moved out front when we use a tensor. So the tensor ordering is row, column, and then you have your quadrature points, variables, and then elements for the indexing. Okay. So that's what we would need to do there. All right, so I've got grad x. So if I have grad x, what I can do is start I suppose what I need to do is loop over all the points and add everything up appropriately. Okay, so that's what we'll do. So we'll do xm grad xl minus xl grad xm. That's on our to-do list. And then we calculate the curl. And if I have the curl, then I can go through and actually fill out the appropriate terms. All right. So that's the sketch of what we'll end up implementing here in the next couple of weeks. Of course, I'll call finalizers for these guys so that we get that in place. But before we get that far into modifying how we're calculating these terms, we need a problem that illustrates, we need an example that illustrates the issue that's at hand. So what I kind of wanted to do is show you how we're going to generate a mesh that has curved sides. Now the one that Coprivi uses in his paper, let me see if I can pull that up right. And let's see here. Let's see if I have that paper. Da-na-na-na. Right, what he had was like this square domain. Let me actually just pull it up on the board here. So what he had, right, was this domain where you have like a square sides, and then we have sort of the sphere in the center. It looked like when I was looking through the Hopper tutorials that there was a mesh that kind of looked like this. So we're going to try to use that guy. So we'll do one like that, and then we'll do like a cube sphere domain. So I started pulling, right before this live stream, I started pulling those in underneath the Etsy mesh. So we have sphere and sphere in cube. Let me go ahead and open these up. So again, you know, a couple weeks ago, I briefly walked through how to do the mesh generation. Essentially, Self is expecting Hopper files as input, so you need to have Hopper in order to process that. Now, I've gone ahead and created a Docker image for Hopper that's available on the Self Fluids Google Cloud project, which if you are a higher order methods open collective member, you can get access to those that way. So definitely reach out if you want those. Of course, you can also find Hopper on GitHub and build it and process these initialization files. So the input here, essentially what we're doing with the sphere case is it takes a square domain and it does really structured mesh generation underneath the hood. and then it blows up the sides of it. So you can think of like as if you were filling up, blowing up a cube as if it were a balloon and having those sides expand into a sphere. But essentially that's what's encapsulated in that parameter.any file. And then the other one here, the sphere and cube, which I've also pulled from their tutorials. It does a square domain, but it kind of looks like what Kopriva had in his paper. So let's pull up pair view to give you an idea of what that looks like. So we have our starting geometry. And essentially what we'll do in our example program is read that in and then try to calculate divergence of a constant flux. All right. So let's go ahead and open up. Let's take a look at the sphere first, which is our cube sphere domain. So we'll look at the spline surface mesh. Actually, you know what? I want to do the volume so we have everything we can look at. Right, so it's just a sphere. If I were to turn on the edges there, right, you can see the element boundaries here, but like logically you can kind of see what I was talking about with the cube sphere approach. What it does, right, is it takes a hexahedra and it inflates it. It maps it out to a sphere. So I put on the debug mesh, which does not have the curved geometry. What you'll see is a cube, or roughly a cube. It blows itself up into a sphere. So that's the geometry, you know, and all of these sidewalls are curved, so they're going to have the curved geometry. So when I calculate those metric terms in my current form, I should have aliasing errors. And if I were to advect aliasing errors around, I should be able to propagate those into a domain if I were to do like a constant advection code. So we'll do that. Let's take a look at this other one that I prepared. This is the square domain with the sphere inside of it. So we'll take a look at the volume mesh. So from the outside, right, it just looks like a cube. Let's put on those edges. It's just a cube, nothing fancy going on. Let me remember what direction we need to rotate this, and we'll do a slice through this guy. Let's put on those edges again. Yeah, so it looks kind of weird when they put it in the VTK format because there's like edges that are connected across these diagonals. But you can kind of make out we have the mesh structure has these like circular elements in the center of them. Now, if I were to kind of wireframe this guy, it might look a little bit better. So let's take a look at that. Let me step back on the number of points here and regenerate that. So let's kill that, and yeah, we'll run Hopper and Docker. Let's go to that workspace. So there we are, and then let's do Hopper parameter.any. Okay, I'll regenerate that just so we can get a better look at this, and let's refresh. It's still not super great to look at, but you can kind of make out the different planes here, and then somewhere in the center of this domain, yeah, we've got our spherical geometry. So we'll try to work with this as our input mesh for the problem. But before we do that, we need to have the model 3D class together, and we need to have the advection code. So this brings me to like the usual thing we've been doing the last few weeks when we build models. If you're underneath the source directory, everything that I've talked to up to this point is what we call the foundation for self. So it's things to do derivatives in computational space. The geometry class gets us to what we call the mapped data class, and the mapped data class is essentially a type extension of the data class, except now we start to bring in things like side exchanges. So once I have that mesh connectivity information, I can actually figure out how I need to do MPI communications for domain decomposition. So that's provided for you. We can do derivative operations, so gradient, curl, and divergence in physical space using those formulas that we derived earlier. That's what's in the mapped data class. Now, one level higher than that mapped data class is the model class. And the model class is where sort of all this stuff gets stitched together to actually solve conservation laws. At the bottom end of the model class, we have time integrators and things that are inherited by every type extension, all the children of the self model. We have methods for reporting, total integrated solution values, entropy, those kinds of things, so you can automatically keep track of the stability of your model over time. Now on top of the model, we have 1D, 2D, and 3D models. So they bring together various mapped scalars, vectors, and tensors to give us the bits that we need to forward step a conservation law solver. And what we're doing today is building on top of this model 3D class, which is actually just now getting added in the last week. We're going to do a type extension of model 3D to do an advection solver. Now, when we first started this year back in January, we actually did a 2D advection solver. So this is actually a good jumping off point for doing 3D advection. So we're going to basically use that as our template to set up a 3D advection solver. We're going to do the CPU side only today, and then we'll set up an example for constant advection on one of those geometries we just looked over. Now, what we'll do, like I said, is we're going to just duplicate this, build on top of it. Now, if you ultimately wanted to do GPU acceleration, you could check out some of the previous videos that I've done as I walk through that quite a bit. Of course, in the coming weeks, if you're keeping track on the repository, you'll see how this comes in play. Essentially, what we do underneath the hood is use a tool called HIP from AMD that allows us to offload to AMD and NVIDIA GPUs. Underneath the source directory, there's a HIP directory where you can write in C++ syntax your HIP kernels, which look almost identical to CUDA. And we provide a wrapper around that kernel so that it can get launched. So I'll give you an example of what that looks like. So just I guess for laughs here, this update grk3 advection 2D. The GPU kernel itself always has this underscore GPU extension to it, and it's going to have this global specifier out front, which indicates that this is a kernel that is run on the GPU, but it can be launched by a GPU thread or a CPU process. The wrapper routine is enclosed by these xtern-c decorators. Of course, we have the same exact name, except now it has the GPU wrapper suffix. And it actually has the chevron syntax to actually launch the kernel. Now, this xtern-c routine is what ends up getting exposed to Fortran using ISO-C binding so that we can launch that GPU kernel from Fortran. We're not going to do a lot of that today. What we really want to focus on is just getting that 3D, those 3D routines defined for the Advection 3D class and demonstrate this particular problem that basically when we calculate the metric terms the way we are right now, we're going to generate spurious noise. So let's go ahead and open this guy up. I'm going to go ahead and do a quick search and replace for 2D, make it 3D, and that gets us most of the way there. Now, every class, when you do a type extension of the model, there's 4 methods you always have to define. And these are 4 methods that are tied to your specific problem, which is why I can't just concretize them for any conservation law. What you need is a way to calculate the source terms. So the right-hand side of a conservation law, what I wrote as Q earlier, that's what goes in there. We have the flux method, which is the method to calculate the conservative flux, the thing we're calculating the divergence of. We have a Riemann solver, which is essentially a method that looks at the faces that are shared by 2 neighboring elements, looks at the jump in the solution on either side, and sorts out how to exchange data between those elements. So like if you're doing a compressible Euler solver, this is basically the solver that figures out how to exchange momentum, mass, and internal energy across that interface. It's incredibly important that you pick a good Riemann solver so that you have entropy stability, which is ultimately what we're building up to. Satisfying the metric identities turns out to be a necessary ingredient to getting there. So this is just one step on that path. Now the set boundary condition is something that you certainly should set. I think the default method that we're overriding, it just sets that to 0, which may or may not make sense for your problem. For example, if you're doing Euler equations, having 0 density or 0 pressure certainly is problematic. So we don't want to you definitely want to at least provide something in this set boundary condition method that makes sense for your problem. Now the other ones that you can override that are useful and allow you to take advantage of some of the other bits in the model class, you want to be able to calculate the entropy so that every problem that you work with, you have some way of tracking stability. So when I say entropy here, what I really mean is a convex mathematical function that combines your prognostic variables in such a way that you're looking at, like for Euler equations, for example, this would be like total energy, so kinetic plus potential plus internal. So you want to have a method that defines that so you can just track stability for your problem. So for the 3D class, all we really need to do to go from 2D to 3D is add a third loop for the quadrature points. So if you're not familiar with self, that's okay. Generally, we have two different styles of loops that you'll see throughout the code. One is what we call a volume loop. A volume loop goes over the elements first, then the variables, the prognostic variables, and then the quadrature point. So if you're in 3D, you'll have a triply nested loop for those quadrature points. Right now we're doing a volume loop because we're doing volume integrals, because the entropy is the volume integral of the pointwise entropy. And we can actually just kind of duplicate some of the things we have here. So wherever I have an ij, I think what I want to do is, I did this before, ij, I want to substitute for ijk, so that's nice. We're going to get another quadrature weight here. So if you ever want to do volume integrals, all you need to do is pull out that Jacobian that you're working with, and then you want to multiply by the Gauss or Gauss-Lobato quadrature weights. It's a very straightforward way to make sure that happens. Whoops. Make sure that comes back. All right, so we got the solution and the Jacobian. So let me explain a little bit, in case you're not familiar, what these structures look like. So if you haven't done object-oriented Fortran before, this might look a little weird. But essentially, with OO Fortran, you can define your own types, and those types have attributes. The way you get to an attribute is using this % symbol. So for example, this, which is the Advection 3D class, which is the type extension of the model class, has associated with it a mesh, geometry, solutions, velocity fields, things like that. We want to pull off the geometry, and underneath the geometry, there's, again, a number of things are defined. One of them is the Jacobian. And then, since everything at the very bottom end is built on this memory class, so this is at the data level. So we have advection level, we have the geometry attribute. That's a data type, a self data type. So it has an interior, a boundary, X boundary, etc. attribute underneath. We want the interior value to get the interior points in the element. And then once you're down at that bottommost level, you either have host data or device data. And the host data are Fortran arrays, device data are C pointers. So that's what we're pulling out here. Same thing with the with the quadrature weights for integration. At the very, very bottom end, we're going to pull that host data right out. And the solution, right? So we have the advection class, we want to get the solution, the interior, we want the solution at the interior points, and then we want it on the host. So that's really what's going on there. So let's look at the next one is a boundary condition. So in 2D, which is what I pulled this from, the boundary loops are over edges, right? So I only have one-dimensional edges for those boundary loops. So I have quadrature points there, but in 3D, my boundaries are faces. So I have 2D faces that I need to do these integrals over. And the number of sides that I have in 3D, since I'm dealing with hexahedra, is 6. It's go ahead and add that J there. Okay. Bump that indexing over. All right. So now when I pull the external boundary, so when you set boundary conditions, what you really want to do is set the ext boundary attribute. Underneath the hood, what's actually going on when we calculate the tendency, I'll pull that up here. Calculate tendency. So to forward step the model, what we really need to do is calculate divergence of a flux and add the source term to it. Okay, so this workflow is defined for every type extension of the Model 3D class here. So we calculate a pre-tendency method, which by default does nothing. We do a boundary interpolation, so it prolongs the solution from the element interiors to the element boundaries. Then we do a side exchange, so it takes care of any MPI side exchanges that you need. Then we set the boundary condition. So after we do MPI exchanges, we can actually set any physical boundary conditions that you have. That's the method we're currently overriding. Then from there, we calculate source terms. We do the Riemann solver. The Riemann solver does depend on what you put in that ext, in that boundary condition, in those boundary conditions that you're setting. So because of the way that ends up working, you just go ahead and whenever you're setting boundary condition, you just set ext boundary. I guess that's the point I'm trying to make here. The easy way to tell if you're at a physical boundary is during the mesh generation process. We have the way these loops are done here is we're looping over the elements and then we loop over the local sides of an element. So since we're doing hexahedra, it'll loop over those 6 sides. Then we loop over the variables, etc. The side information, part of the side information is what we call the secondary element. So no matter what, if we're thinking in the context of I am element IL and I'm at side I side, what I want to know is the element ID for my neighbor. If I don't have a neighbor, that secondary element ID is set to 0. There is also another index you can use to pull out a boundary condition flag in case you have multiple boundary condition types. A good example of how that's done is to look at the shallow water 2D. I guess it's just shallow water. Let's take a look at the boundary condition method. In case you need to work with multiple boundary condition types, underneath the mesh is the side info array. So the 5th index in there, this is all documented in the mesh class, by the way. You can pull out the boundary condition ID in case you have integer flags that you're using. And of course, that neighboring element side is that 3rd one. So if the secondary element is 0, you want to set a boundary condition. And then of course, if you have a particular boundary condition ID that you're using, you can put up some logic to swap between different boundary conditions that way. Right now, I'm just going to do a simple advection problem where I'm just going to try to bring in no data from the boundaries. So it shouldn't really advect anything in. So we'll just keep it simple here. I think that's all I need to do. So do that source term. So the source term is a volume style loop. As we're looping over point by point in the mesh. All we need to do is add a K loop, and then we'll swap out IJ for IJK. For the flux, we're going to do the same thing. We're doing a volume loop. Okay, so I'm just going to add that loop there. Again, I'm going to swap out my IJs for IJK, and because we're now in 3D, I have 3 components of velocity here advecting things around. We'll go ahead and add that 3rd one. All right. So that's looking good. So I'll give you a quick rundown here. What we're doing is calculating the flux term, which for the advection solver, right, is u vector multiplied by the solution. So the first dimension, you can calculate these in physical coordinates. Part of that calculate tendency process is it will map all this to computational coordinates for you, so you don't have to. So this first one here, oops, if I were to write the vector as u in the x hat, v in the y hat, w in the z hat, this is u times the solution. This is v times the solution, so the y component, x component. And this third one is the z component. Just taking that, z component, and this is w. All right, so it's the third component of the flux vector is the third component of the velocity field multiplied by the solution. Okay. Now we've got our Riemann solver. So again, the Riemann solver is a boundary style loop. So we have loops over elements, then loops over the sides, then we have loops over the, of course, the variables and the quadrature points. And the quadrature points again, when we're working in 3D, these are 2D faces in 3D space, right? So let's go ahead and let's convert our I to I comma j's. So we got that. Get our n hat out of here. It's looking good. Get that velocity field. In case you missed what's going on here, so the Riemann solver, what we're essentially doing is an upwinding method. So what it's going to do is calculate u dot n hat at the boundary, and then it's going to figure out which solution we want to use to make sure we have an upwind method. So the question is, do I use the element or the solution from the primary element or the secondary element? And that depends on if the flow is going out of or into the primary element. So that's really all that's going on here. Nothing too crazy. Linear advection is fairly straightforward for this kind of problem. So once we have the normal velocity, we pull the external state, what I call the secondary state, the internal state, the primary state. We've got the magnitude of that boundary vector, so we can do an area integral. That's down there. And then essentially what we do is we do an average of the flux, so un dotted with the times the internal plus the external state, divided by 2. And then we subtract off the absolute value times the jump in the solution, and that gives us the upwinding that we want. So let's make sure I've got a do loop closure there. So I got 1, 2, 3, 4, 5, and I've got 5 loops up top. Great. So that's it in terms of the things we need to set for making an advection solver. Fairly straightforward, so long as we're not doing anything on the GPU, which we're not. Now the next step to put this into the build system, you're going to go into the root directory of self, modify make.include. What you want is the F90 sources if you're adding a new module. All right, so we'll do self advection 3D. Okay. If you were adding the GPU accelerated kernels, you would also add self advection 3D in this case to the self CPP sources. So we're going to give this a compile check, make sure that works, and then we'll move on to writing an example, and we'll add the example to this examples list. Now the way I'm building here today, so there are a couple methods to install self. This install script that's included, actually I should back up. There's a few dependencies that self has. And those dependencies I've provided for convenience a SPAC environment file. So if you're using the SPAC package manager, you can set up an environment that you can use to build self. It does require that you have HIP and CUDA installed on your system locally, since building HIP with SPAC is quite buggy right now. So installing HIP from apt or yum, depending on your Linux distribution, is preferred. And then of course installing CUDA following NVIDIA's installation process is ideal. Once you have those, you can install the environment for self just by running basically spac env activate, I believe. I'll refer you to the spec documentation, but essentially you'll activate the environment with this YAML and then just run through a spec install to get those packages in place. You could do that. The other option is to use the Docker containers, the Docker recipes that we have. So there's two stages to the build process. One is the base build, which essentially sets up a container that has all of those dependencies installed. That process takes about an hour, hour and a half to complete, depending on your system. Once you have that base container, you can reuse it over and over just to build self, which only takes a couple minutes. Now, all those container images for self base, and of course the self builds are hosted on the Self-Fluid's Google Cloud project. And so what I actually end up doing is following a build recipe using Google Cloud Build in those containers, which you can also do on your local system. So provided you have those base containers, underneath that CI directory, there's a couple of what we call build pipelines. The local one is what we're going to run. So this is just a YAML that defines the steps to build the self container. So we have the Docker build, and then we're going to run through some tests here. And I think, is that accurate still? I may need to adjust that a little bit, but that's all right. Actually, no, because the test.sh is still there. Okay, great. Now, the way you run those builds locally is just by running cloud build local. So this requires installing the gcloud SDK and then the local builder tool that goes with that. We're going to pass to it that cloud build local pipeline, and then I don't want to do any substitutions. I'm just going to build it with the defaults. But if you did want to build a container for AMD GPUs, you could do that. So we'll go ahead and let that run for a minute. While that's running, let's go ahead and start working on our example to demonstrate this breaking process. So I'm going to start from that advection conservative form block mesh 2D. And what we're going to do here is, let's do the sphere mesh to start. Okay. Go ahead and pull up that sphere mesh here. Okay, so again, we'll just do that 2D to 3D conversion, make that easy on ourselves. There's a lot of things that we're going to take advantage of because we're starting from one of the existing examples. So one, and this is coming up in a few weeks here, I'll show you how we actually put in a command line interface using JSON Fortran. So you can actually just change your command line interface for self by modifying a JSON file rather than writing anything in Fortran. We'll use the default command line interface, which provides a lot of useful things out of the box for us. Things that control time stepping, so how frequently we output files, how long we want to integrate for, what the time step size should be. These two toggle on or off MPI or GPU acceleration, those kinds of things. What we want to do, the environment variable self prefix is used to figure out where some of the default meshes are. And it also is used to figure out where that JSON file is for configuring the command line interface. So during the build process, that self prefix variable gets set inside of the Docker container for us. So that's useful. When we go to read in the mesh down below, so of course, once we parse the command line, we'll initialize a domain decomposition, we'll initialize interpolants, and then we'll go ahead and create our mesh. The mesh we want here today is, I think, sphere, and I think I just called it sphere. Was it just sphere mesh? Let's take a look. I'm in the wrong directory. Let's go back to sphere. that is just going to be a sphere mesh.h5, all lowercase. So let's go ahead and get that. Looks like we got a few errors to fix, but we'll take care of that in a minute. All right, so that's that. We're going to go ahead and take advantage of the decomposition generation. Down below is where we actually set the velocity field. So I'm just going to do something simple. We'll just advect in the x direction and nothing else. So a constant velocity field, and it's real easy because it's in one direction. And I'll actually show, hopefully today, that this still gets us, it's a pretty bad looking solution. We'll set the tracer field to 1. So we have a uniform tracer field to start, and we're going to advect everything one way. And because the mesh is curved, and we don't satisfy the metric identities, this should generate some noise for us. William asked, does self use the HDF5 library? And yeah, we absolutely do. So there's a couple things we use HDF5 for. So one, let me clear this up. So underneath the source directory, there's like basically a wrapper module. It does some really basic stuff for handling file I/O and serial and parallel with HDF5. The reason I put all this stuff here was because we can work with all the different types in self memory fairly straightforward with the and having the same kind of interface. There are some ways I can clean this up a little bit using what are they called? It's when you use, I can't remember the name for it. Maybe you remember. It's when you use this kind of declaration for the input. So we can kind of work with more templates, but at any rate, the idea here is we have methods for reading and writing attributes, reading and writing arrays that, as you can see, there's a ton of them for working with different data types in self. And those end up getting used for like the mesh. So when we actually read a mesh in, so like for example, read Hopper, those Hopper mesh files are HDF5. So reading Hopper Mesh 2D, it leverages all that stuff in that self HDF5 module to pull in the various bits that we need. The beauty of that is doing things in parallel, which you can see I'm actually cleaning up here at the moment. All I have to do, the way I've set up the interfaces, is if you pass in a domain decomposition on top of the thing you want to read in, and so the domain decomposition defines the MPI rank and stuff. It'll figure out what slices through that file to actually read in for you. The output as well for self, so underneath the model class, is also HDF5. So we have two different types of output right now. So when you go to write the model, let's see here. Let's do something interesting here. So write model 3D, for example. It's again going to use a lot of those HDF5 methods to write the data out for the model. And when we write to the HDF5 files, what we're really writing is the data stored on the quadrature points. It's really meant for doing like file restarts, or if you want to maintain spectral accuracy in post-processing tools. That is what you end up wanting to use. Now, if you're just wanting to do quick visualization, we do have tecplot output as well. And the tecplot output is primarily what I end up pulling up in ParaView. But yeah, thanks for asking. And where were we? Right, so we were in the advection, and what we're gonna do is, I'm just gonna go ahead and set that to RK3. I'm kind of tired of that Euler integrator, not really stable. Right, so yes, this is what we'll do. So we're just gonna build, right, so this example we'll add to the make system here once we fix the other problems. This should read in the sphere, and if we forward step by a few time steps, what should happen is the initial entropy, the entropy is gonna grow. And the reason why I know it's going to grow is because if I start with a uniform field and then I add noise to it, because of lack of satisfaction of the metric identities, I will get non-zero perturbations added to my solution. If I square those values and add them up, the entropy should change. And in fact, it will grow because I'm going to be continually adding non-zero divergences in the metric terms to the solution over time. Okay, so we do have those checks below. If if the entropy is a nan, we'll go ahead and throw an error. If it's infinite, we'll throw an error. If the entropy later is bigger than the initial entropy, then we'll at least throw a warning. So that's what should happen. Let's go see what we broke in the code. So that's, all right, not too many things. So self-advection 3D at 132. J cannot be redefined. I put 2 J loops. One of those should be a K loop. And we wanted advection 3D. What was that? That was 132. All right, so yep, there it is. Silly mistakes. And then I accidentally typed the letter Y rather than 6 in doing that side loop. So let's go fix that. All right. And the last one here is a dimension mismatch. I've got n hat 1 to 3 on one side and 1 to 2 on the other. So let's go ahead and fix that guy. All right. Let's give that a build. So right now we're still not running the example, but we're just going to make sure it builds. To get the example added, to that build system, which automatically adds it to our testing infrastructure, all you need to do is once you have that example defined, which look again at that directory, what we want is the name of the file without the extension. And we're going to drop that in the examples list. That's really it. So once we're certain that this builds just fine, we'll go through, we'll rebuild with the example in there, which should run the example, and we'll see if the entropy increases. I'll also show you, if we could prove that, then what we'll do is we'll launch a Docker container for self, and run that example and actually generate some output using the command line interface. And then we'll take a look at that in ParaView, see what we get. Because we should see something similar to what Kopriva showed in his Euler problem. Now, of course, he's doing a different system of equations, so those errors propagate differently. But I at least should show, one, there's error generation wherever the grid is curved. And since I'm advecting things from left to right here in the positive x direction, those errors should propagate in that same direction. So we'll see if we can pull that off and demonstrate this issue. Because if we can, and we think we have a solution for it in the next week or so, I'll be able to give that a try. So looks like all the other tests are currently running, which is good. So part of this testing process, right now I only have the testing infrastructure here set up to run in serial on CPUs. I'm working on some extensions using a tool we wrote called Fluid Run, or RCC Run. That tool will be used to do some testing on GPU architectures and on clusters. So we could start automatically benchmarking things and trying out the code on various hardware. But looks like we're good there. So we're going to do that run one more time now that we've got the examples in there. And now that the example's in there too, we'll be able to launch that self container to mess around with that example problem and generate some output to look at. So while that's building, I might as well show you a little bit about how this is working at the moment. So remember that CI cloud build local.yaml. What it's doing is it's building the container, and then it's running this test script. So that test script So I'm assuming that things are being built in this case with coverage enabled with the GCC compilers. And basically it loops over all the binaries that are in the examples install directory. It actually runs the file, checks the exit code. If it fails, it's going to fail fast. So if any of the example fails, it's going to stop right away. Provided it exits with a 0 exit code, we kind of merge together the GCDA and GCNO files that are created to create JSONs for the coverage reports, and then those all get merged together using gcovar, which ultimately, when we do like pull request build, so if you were to look at the CI for a pull request, we do the same thing. We run test.sh, except then we also send that data up to CodeCov so that those coverage reports get posted to a pull request, which is pretty helpful for automating that process. Okay, so we have a few issues here to work out. So I've got, all right, I didn't fix the geometry, so let's go check that out. So we got examples, advection, sphere. So the geometry, there it is. SEM quad should be SEM hex now. I need to have the velocity field go from 1 to 3. That's definitely going to be part of the problem. So that should take care of this. That should take care of this. Now the velocity field, because I had a different shape, I see this is a red herring down below. So that should, I think that fixes all of our problems. Yeah, give that a go. Almost there. Pretty excited to show you how we can break things. It seems to be something I'm pretty good at. Now, fixing them takes time, of course. So we'll get there in the next couple weeks. I suppose one thing I could share is what we've got going on while that builds. There's another branch on Self at the moment if you're interested in learning more about how we're doing benchmarking. One, I'll make a plug here for the Improving Scientific Software Conference coming up April 4th through 8th. It's run by NCAR. It's free to attend. You should check it out. We'll be doing some tutorials there on how to do automated benchmarking. Let me go ahead and pull up this branch here. We've got a new build pipeline coming in. It's going to do the same thing. It's going to make a Docker image. We're going to convert it to a singularity image, which will get posted to another container registry. So, the idea being, as we produce these artifacts, these become available to folks who want to run Self without having to worry about building it. We're using this tool. It was called Fluid Run. We've changed the name recently to RCC Run, but what it does in the background for you is spin up compute resources on Google Cloud, things that have like GPUs attached, or if you want to run on multiple VMs, things that you're not going to get with like GitHub Actions. And it'll run through a series of tests and log the run times, memory usage, and a few other factors, so you can keep track over time with each commit to the repository what the performance looks like and how much of the resources you use. The other benefit here is, especially when you're on cloud, is there's a variety of hardware available, so you can start to assess what kind of hardware your code runs well on out of the box, which ones might need more attention if you're interested in things like performance portability. We are working on some integrations to get this tool to work if you have a Slurm cluster on-prem as well. We're working on some ways to try to get that to connect there. So pretty exciting stuff. I'm looking forward to getting this added into Self here in the next couple days. So we're just near the end on that branch, but yeah, if you're interested in following that along, check out that feature benchmarking branch. And I believe pretty soon, actually I do have the PR open now, so if you're interested in getting involved there, don't hesitate to reach out. Looks like we ran, but we broke some things. So let's see, what did we break? Looks like I've got a little bit of a bug in the hopper mesh read in serial. Let's take a look at what's going on there. If it looks like it's going to be too lengthy of a bug, I will cut this early and get back to you guys on what's going on. But let's take a look here. We're going to take a look at this particular problem. It might be that this mesh does not have all hexahedra elements, which I might need to go fix. But let's see. Set self mesh 1353. So it looks like the neighboring side is coming back as 0. Huh. What I might do is change that conditional. So what we really want here is to only recalculate. So this is an interesting thing when you're dealing with unstructured meshes. The problem is when you describe an element, you'll use a particular ordering for the nodes. And the way we do it in self is following what's done in CGNS and following what's done in Hopper. But you number the nodes, so what we call the bottom is nodes 1, 2, 3, and 4, where 1 is in the southwest corner. Then we go southeast, northeast, northwest. And then the top 4 nodes, again, starting southwest, but now on the top to the east, northeast, and then northwest. They have 5, 6, 7, 8. Now, if I have 2 neighboring elements and they share a face with each other, I could have a whole bunch of scenarios going on. I could have the bottom of this element being the east wall of the other element. And weird things can happen, but essentially what we need to do is figure out the relative orientation of the metric terms between those neighboring elements. That's what this recalculate flip method is doing. So it's essentially saying, are the metric terms parallel? Are they perpendicular? Are they anti-parallel? Are they anti and perpendicular? So there's those 4 possible combinations. So that's what this is doing here. And we only want to recalculate this flip parameter. So how many of those rotations I need to do to get things to line up for interior elements. BCID being 0 might not have been the best choice. So I'm going to give this a shot and see if that fixes the problem. You could tell it's been a minute since I've used the 3D modules. The last few weeks we've been working mostly 1D and 2D, so this will be another good step in the right direction. I believe the next tutorial we have is on doing the Euler equations. We'll start in 2D, and then we'll do 3D as well. So we'll actually start to build out some pretty cool solvers here. Of course, outside of the shallow water stuff we already have. And we'll see what we get here. Yeah, I'll say if you're tuning in and you did have any comments, suggestions, things you want to see, you can drop them in the chat. But of course, to drop a chat in there, you just do need to hit the subscribe button on the channel. I'm happy to entertain anything you guys want to see in the spectral elements world, in the computational fluid dynamics world. I think after we do the Euler solver, we're taking a little bit of a break from spectral element theory, and we'll be diving into how to use the poor man's argument parser, FLAP, which is a Fortran library for doing command line interfaces, and JSON Fortran. It'll be going over a bit of how we put together the command line interface for self, how that works. And we'll be doing a very interesting detour into how to interface with Arduinos in Fortran, which is a lot simpler than I thought it would be. So I'm hoping that stuff is going to be interesting for you guys. But if you have any thoughts, definitely let me know. All right, Looks like we still got an index of 0 at the same point. I suspect the mesh I have coming out of Hopper might not have all hexahedral elements, so I need to go fix that. Stay tuned. I'll be posting some stuff up on Reddit here in the next week or so and up on YouTube demonstrating this error once I get all this figured out. But thanks everyone for tuning in. I hope you found it useful, and I'll see you guys in 2 weeks.